Hi everybody, I hope this video finds you well. In today's video, we're going to be starting into section 1.6 from your textbook, which introduces us to the next type of first-order differential equation that we're going to learn how to solve. This is going to relate to one of the topics that we talked about at the very beginning of our course, which was what a linear differential equation is. As I mentioned at the beginning, we're going to do a very extensive study of linear differential equations of all orders towards the end of our class, but for right now, we're going to just focus on first-order linear differential equations and see that we can come up with a very sort of nice general technique for handling this type of differential equation. So recall we had this definition, and I think we gave this definition in general for any order linear differential equation, but now again we're going to focus on first orders here. So just as a reminder, a linear first order differential equation is said to be in standard form if it is written as follows. You have y prime plus p of x y equals q of x. Remember that basically what we're saying here is that in general, the definition of a linear differential equation is that there can be no functions of the dependent variable or any of its derivatives, and each instance of the dependent variable and all of its derivatives must be in separate terms. For it to be in this standard form, though, what we really want is we want the y prime with no coefficient function of the independent variable, basically the y prime just to be isolated by itself. So we have this sort of format here. So we're going to talk a little bit about exploring how to solve this type of differential equation. Then we're going to summarize the method that we sort of deduce, and then we'll take a look at some examples here. Now, if you guys sort of think back to the main technique that we've talked about so far, which is how to handle a separable differential equation, you'll see that that doesn't work so well in this sort of general form for a linear first-order differential equation. And the reason is that we're not going to really be able to separate that p of x and y because there's no y on this, so bringing this over and then trying to factor something is in general not going to work here. So this is definitely a different type of differential equation than the ones that were separable. If you think about what we did with separable, though, the idea was that if we could get all of the stuff that was a function of y on this side and everything that was a function of x on this side, then we could integrate both sides with respect to their respective variables. So we'd integrate the left-hand side with respect to y, right-hand side with respect to x. Again, we don't anticipate in this format being able to separate x's and y's. So we'll notice, though, that in this standard form, this right-hand side would be very easy to integrate with respect to x because, well, it's just a function of x. So it would be nice if we could think about the left-hand side as also a derivative with respect to x. So the sort of technique that we're going to explore here is what's called an integrating factor technique. And we'll actually see these several times, and if you guys ever take a more extensive course in differential equations, you'll see them many, many more times. But the idea of an integrating factor is basically something that we multiply on both sides to create a derivative formula basically on one of the sides of the equation. So what we're going to actually do is we're going to start with this equation and we're going to see what sort of integrating factor might be useful. So we're imagining that we have this sort of setup, y prime plus p of x y equals q of x. And again, our goal is that we know that we could integrate this side with respect to x very easily. This is just a function of x. So we'd like to think about this as a derivative with respect to x. So if we look at this, this sort of already resembles a product rule. So what we're going to try to do is we're going to try to make it so that it satisfies the product rule for derivatives. What we're going to do is we're going to multiply both sides of this equation by this integrating factor, which is e to the integral of px dx. So we're going to multiply both sides by this e to the integral p of x dx, where this p of x, of course, references that p of x there. Now, it might not be immediately clear why this is useful, but let's take a look at what this does. So if we do that, we get the integral px dx y prime plus e integral px dx p of x y equals q of x. Equals e integral px dx qx. Okay. Notice right-hand side, still a function of x. So we only have a function of the independent variable on the right-hand side. Now, the claim is that this left-hand side can actually be thought about as the derivative with respect to x of a particular function. In other words, that this left-hand side is actually a product rule. So we're going to take a look at this. We're going to actually claim this is actually the derivative with respect to x of e integral p to the x dx y. And let's see if that actually makes sense. So if you were to actually perform the sort of product rule here, remember we're treating y as a function of x. Y is the dependent variable here. So by product rule, you would differentiate this piece times this, and then you would add this times the derivative of this. So let's see what we would get there. We'd get something like the derivative with respect to x of e integral px dx times y plus e integral px dx derivative with respect to x of y. So that's just a product rule there. Okay, now this first term is a little bit complicated, but we can go ahead and do this using chain rule. The derivative of e to anything is still e to that same thing, px dx. And then by chain rule, we take the derivative of the inside. The derivative of the integral of px dx by fundamental theorem is going to be px. And then, of course, we have y. All right, notice that this right here resembles this. Okay, perfect. And then here, well, the derivative of y, well, we just call that y prime. So that's e integral px dx y prime. So we will notice that this left-hand side is actually the derivative with respect to x of this product. So this integrating factor is exactly what we need to multiply both sides by to make the left-hand side equivalent to the derivative of this product. So what's the advantage of this? Well, what that means is that we can rewrite this as this derivative. So we can actually say now that we have the derivative with respect to x of e integral px dx y is equal to this crazy e integral px dx qx. Now, the whole point of this is that now this left-hand side is the derivative with respect to x of some product, and this right-hand side is a function of x. So we can integrate both sides with respect to x. So integrate both sides with respect to x. This is very different than what we did for separable differential equation. For separable differential equations, we basically proved that since one side was a function of one variable and the other side was a function exclusively of the other variable, we were allowed to integrate both sides with respect to different variables. In general, you cannot do that, right? It would not make sense to be able to integrate two sides of an equation with regards to different variables. For separable, we proved that in that special case, it was allowed. But in general, if you're going to differentiate, integrate, or do anything, it needs to be the same thing on both sides. So in this case, we're going to integrate both sides with respect to x. On the left-hand side, that's going to be very easy because the integral of the derivative is just going to be the original function. That's fundamental theorem. So there we go. And on the right-hand side, we get the integral of e to the integral px dx qx dx. Now, this might be very messy to do, but it's something we can attempt to do. It's the integral of a function of x with respect to x. So maybe not easy to do, but it is doable, right? Or at least where you can express it in this form. Now, in your book, they go a step further and they show how you can divide this over and actually get an expression just for y. I'm not particularly interested in that because I don't like a really messy general formula. Instead, what I want you guys to really see here is that this gives us an approach for solving any sort of first-order linear differential equation. So this basically is where we're going to call it good here because this shows that we can handle solving for y. Notice there's no derivative of y left in terms of just an integral of some perhaps very messy function of x. All right, let's go ahead and summarize this and then start to take a look at some examples of how to do this. Again, if you do read this portion in your textbook, you'll see that they go all the way to a general formula for the solution. They say y equals something. I don't really particularly like that because, again, I'm more interested in the technique rather than just sort of the formula that comes up at the end. But, of course, if you want to try to use that formula approach, you're welcome to do so. All right, let's summarize, though, what we just saw in this exploration. So, in general, if you have a linear first-order differential equation, and it is in standard form, so you got to make sure you've put it into standard form, Then, if both that p of x and q of x are continuous on the interval I, so as long as that p of x and q of x are continuous, then the general solution to this equation can be found as follows. If you multiply both sides of the equation by the integrating factor, that is e to the integral px dx, so you take this p of x, you integrate it, you do e to that, and you multiply both sides of the equation by that integrating factor, then the left-hand side is guaranteed to be the product rule derivative with respect to x. So you can rewrite the left-hand side after multiplication by the integrating factor as a product rule with respect to x. And then, since the left-hand side is a product rule with respect to x and the right-hand side is a function of x, you can then integrate both sides with respect to x. And then you can do any sort of algebraic manipulations you want from there. So, again, as I mentioned, if you look in your textbook, you can find just sort of an end formula, but I prefer this as a sort of technique because I think it makes a lot more sense as a series of steps rather than just jumping to some sort of complicated final answer. So, in our examples, we'll always sort of be using these 3 steps. And technically, you should imagine that there's sort of a preliminary step of making sure you put it into standard form. Once it is in standard form, you multiply by the integrating factor, rewrite the left-hand side as a product rule, and then integrate both sides with respect to x. Okay, let's get in and take a look at some examples here. So, for our first one, we're going to try to find all the solutions to this differential equation, y prime plus 3x squared y equals x squared. Notice, even if we weren't in section 1.6, we would sort of recognize this as linear, y prime and y, no functions of the dependent variable or any of its derivatives, and the derivative and the dependent variable show up in separate terms. So this is linear, and it is already in standard form because there's our p of x, there's our q of x. So we can immediately move into our technique. Our integrating factor is going to be e to the integral 3x squared dx. So we take that p of x there and we integrate it. And that's going to give us e to the x cubed. So we get e to the x cubed. We don't need to use plus c because we're just choosing any antiderivative here for the integrating factor. So you might as well use the one with the c being 0. So we don't need to put like a plus c up top or anything. For your integrating factor, you're just choosing one single antiderivative. Now that we have the integrating factor, we multiply both sides of the equation by the integrating factor. So we get ex cubed y prime plus 3x squared ex cubed y equals x squared ex cubed. Now, if you calculate this integrating factor correctly, in other words, if you don't make a mistake in the antiderivative, this left-hand side is guaranteed to be a product rule. Well, we can actually just confirm that. We should be able to see that it is the derivative of ex cubed y prime. It is always going to be a product of the integrating factor along with y. Can you manually check this? Sure. You take the derivative, apply it to the ex cubed. That's going to be ex cubed times the derivative of x cubed, which is 3x squared, and then times y. Notice that that's that term. And then you distribute the prime to the y, and you get ex cubed y prime. That's this term. So this is exactly the derivative with respect to x of this product. So we have this equal to x squared ex cubed. Now we integrate both sides with respect to x. So just put integrate with respect to x. The left-hand side, since it is already the derivative with respect to x, we just remove that derivative. And on the right-hand side, we get the integral x squared ex cubed dx. How do we actually do this integral? Well, probably easiest to do this as a quick u sub, u equals x cubed. We identify that there's a need for a u substitution because we have a composition e to the x cubed. Du is going to be 3x squared dx, which means we're going to get a factor of 1/3, so we only have an x squared dx. We get ex cubed y is the integral 1/3 e to the u du. Now we can go ahead and finish our integral, 1/3 e to the u. Make sure you put your constant of integration, and then resubstitute. Ex cubed y equals 1/3 e to the x cubed plus c. Can you go ahead and actually get an explicit form for y? Sure, not too hard, just divide this over, so it's not bad to do that. And if you do, it looks like you should get 1/3 plus c e to the negative x cubed. Because if you divide this over, It's basically c over e to the x cubed, which of course you can think about as a negative exponent. So there we go. There's our general solution, and since we didn't do anything along the way of like dividing by a function of y, we know that there aren't any other solutions, so this is the general solution here. So there we go. There's your guys' first example of going through and solving a first-order linear differential equation. Now, just out of curiosity, if you want on your own, you can go back, and if you take a look at this thing, there's actually a way to solve this without using all of this. This one actually turns out you could separate it because of the fact that these both have x squareds. You could have rewritten as y prime is x squared minus 3x squared y. Then you could factor the x squared, get x squared 1 minus 3y, divide this over, and then actually use our separable approach. So just because you use one approach does not mean that the other approaches don't work. Now, in our later examples, we'll see that actually they are non-separable, so they are sort of forced to do them the linear way. But in this one here, if you identified it as separable by bringing this over and factoring, you could do it that way as well. So just like with integration, there are sometimes multiple ways to approach a single differential equation. All right, let's take a look at another one. So we're going to try to find all the solutions to this differential equation. Y prime minus x to the fourth e to the xy equals 3 over xy squared. Now, as soon as we see this, we might think that maybe I made a typo or something because this is nonlinear, right? The y squared, that makes it nonlinear. The y times y prime, that makes it nonlinear. So we've got definitely some pieces here that are nonlinear. So right now, this thing is nonlinear. If something's nonlinear, there's no hope that it somehow is linear, right? Either you're nonlinear or you're linear. But notice that there is a modification that would change this from a nonlinear differential equation into a linear one. In fact, all of these terms have a factor of y. So let's divide everything by y. If we do that, we get y prime minus x to the fourth e to the x equals 3 over xy. But when you do that, you are changing the differential equation because we know that this division only applies if y is not equal to 0. So we will need to check y equals 0 as a potential solution at the end. All right, now let's look at this. Notice that there's the y prime, there's the y. No functions of the dependent variable, so this is linear now. So this thing here, this is linear. However, it is not in standard form because we need this thing over here and we need this piece over there. So let's go ahead and do that. So we get y prime minus 3 over xy equals x to the fourth e to the x. Now this is linear and in standard form. So we can approach it our new way. So we're going to create an integrating factor. The integrating factor is going to be e to the integral. The p of x here is not just 3 over x, it's negative 3 over x. It's the entire coefficient there. So make sure we get negative 3 over x dx, which of course is going to be e to the negative 3 ln absolute value x. Here, we can do a little bit of manipulation. First of all, it's actually unnecessary to use the absolute value here. We can just say ln of x, because again, we're choosing just a single antiderivative, so we don't have to worry about the absolute value there. This simplifies. You can't just simply cancel out the e and the ln. Instead, you have to be a little clever. We've got to view this as e ln x to the negative 3. And of course, you can bring a value outside of a logarithm as an exponent. Now we can cancel those out, and we can see that our integrating factor is actually x to the minus 3. So we're going to multiply both sides by x to the minus 3. So let's go ahead and do that. We get x to the minus 3, y prime. And of course, when I multiply it onto this, it might be easier to think about it as minus 3x to the minus 4, y. And then when I multiply it on this side, I get x e to the x. Now, if we've done all this correctly, this left-hand side must be a product rule of this integrating factor and y. So this left-hand side should be x to the minus 3, y prime. I always recommend just taking the moment to check it. Derivative of x to the minus 3 is minus 3x to the minus 4, and then you leave the y alone. That's that term. And then if you leave this alone and differentiate the y, you get that right there. So this really is equivalent to this there. Now, this is a derivative with respect to x. This is a function of x, so we integrate with both sides with respect to x. So integrate with respect to x. We get x to the minus 3y is the integral x e to the x dx. This right-hand side is an integration by parts. So let's just remind ourselves how to do that. We can let the u be equal to x, the dv be e to the x dx. How do we know this is a good one for integration by parts? Well, remember, integration by parts is often used when you have a product of functions and you can't get away with like a u sub or something. So as soon as we see that product, we're thinking integration by parts there. Our du is then dx, and our v is e to the x. So we get x to the minus 3y. We do our uv, which is x e to the x minus the integral. Our v du, which is e to the x dx. Remember, you still got another integral to do, so we'll finish that up. X to the minus 3y, x e to the x minus e to the x. Pop our constant of integration on there because we finished integrating. And again, not bad to get a y in an explicit form. Let's multiply the x cubed over, and we get y is x to the fourth e to the x minus x cubed e to the x plus cx cubed. So there we go. There's our solution, right? There's our solution to that linear equation. Now, this would be the general solution if we had started with this. But we actually started with this nonlinear one, and we made this decision to divide through by y, so we need to check this. So let's go ahead and do that. So let's check y equals 0. So if y is equal to 0, then the derivative is also equal to 0. So this side is going to be 0 and 0. The right-hand side is also going to be 0. So left-hand side, 0. Right-hand side, 0. Do we care that there's zeros? No, we just care that this and this are always going to be equal. So this works. So y equals 0 is a solution. If we go back down here, well, I can choose any constant I like for c, so I could certainly choose like c to be 0 and get rid of this, but I'd still have all this stuff there. So there's no way to include y equals 0 in here. So our solution set must be this entire family, x to the fourth e to the x minus x cubed e to the x plus cx cubed. Got to have all those things, and we have to include y equals 0. Should we call this a general solution then? Absolutely not. There is no general solution to this differential equation because we have this entire family, but we also have something that does not fit this family that is also a solution. You might say, well, didn't we say that linear differential equations always have general solutions? Well, we did say that, but unfortunately, remember, the initial differential equation we started with was actually nonlinear. So if we had started with this, then yes, it would have this as its general solution. But our nonlinear one that we actually started with before modifying by dividing by y actually does not have a general solution because it has that whole family along with that y equals 0. Okay, so a little bit more interesting here because the integrating factor, there was sort of an algebraic simplification. This is something you guys are going to see a lot of. Anytime you end up with like an ln after that integral there, make sure you manipulate it appropriately to simplify that integrating factor because that's going to usually make the next integral you need to do much easier. If we had just kept that thing as e to the negative 3 ln x and we had just put that over here, it would be very hard to actually do that integral. All right, let's take a look at another example here. So we're going to try to find the unique solution to this IVP. So again, we have a differential equation, but now we also have an initial condition. We also are getting this piece of information that we know it has a unique solution. So the problem is telling us there's only one solution. We just got to find it. Is this thing linear? Well, y prime and y, separate terms, no functions of the dependent variable. So we should make a note. This is definitely linear. Is it in standard form? No. This thing is on the wrong side, so we got to shift this over first. So y prime plus 4 over xy equals 1 over x to the fifth plus 1. Now this is in linear standard form there. So we're all good with that. Okay, so we're ready to go ahead and find our integrating factor. So our integrating factor here is going to be e to the integral 4 over x dx because there's our p of x. Integrating that should be pretty easy. That's going to be e 4 ln x. And then, same trick, we can put that 4 in as an exponent, so e ln x to the fourth. and then we can cancel there and get that to be an x to the fourth. So our integrating factor is actually x to the fourth. Let's multiply both sides of our equation by x to the fourth. So we get x to the fourth y prime plus 4x cubed y equals x to the fourth over x to the fifth plus 1. Now, again, if we've done everything correctly, the left-hand side must be the derivative of a product. We can check. It should be x to the fourth y prime, always integrating factor in y. Again, though, it doesn't hurt to just check to make sure we didn't make any sort of arithmetic error. Derivative x to the fourth is going to be 4x cubed with the y, and then plus. Leave the x fourth alone, and we get the y prime. Yep, that's right there. Now, this is a derivative with respect to x. This is a function of x, so we can integrate both sides with respect to x. So integrate with respect to x. That means on the left-hand side, we get x to the fourth y is the integral x to the fourth over x to the fifth plus 1 dx there. How do we integrate this right-hand side? Well, we can go ahead and do a u substitution here. U equals x to the fifth plus 1. du is 5x to the fourth dx. We'll have to get a 1/5 du is x to the fourth dx here. So we can go ahead and pop that stuff in. We've got x to the fourth y is now going to be the integral 1/5 1 over u du. Let's go ahead and integrate that then. So we get x to the fourth y is 1/5 ln absolute value u plus c. And we can pop the u back in. So we get x to the fourth y is 1/5 ln x to the fifth plus 1 in absolute value plus c. Okay. Now we could get an explicit form for y by dividing by that x to the fourth. So we get y is 1 over 5x to the fourth ln absolute value x to the fifth plus 1 looks like plus c over x to the fourth. Okay, so there's our general solution for this thing, but we wanted the particular solution that satisfies y of 1 equals 0. So let's go ahead. We won't go all the way back up to the top so we can just sort of see it. We want y of 0 to be equal to 1. Or sorry, no, other way around. Y of 1 is supposed to be 0. So that means when x is 1, y is equal to 0. Let's throw that stuff in. 0 is going to be 1/5 ln 1 plus 1 plus c over 1. So it looks like we get 0 is 1/5 ln of 2 plus c. So it looks like c is negative 1/5 ln of 2. So that means our unique solution that we were looking for is y equals 1 over 5x to the fourth ln absolute value x to the fifth plus 1 minus, what is that, ln of 2 over 5x to the fourth. So there we go. There's our unique solution with that c plugged into this component here. So that gives us our unique solution to the IVP. So just wanted to do this here, not really anything too different because the technique for solving it was the same thing, this integrating factor, but just to make sure you guys are still comfortable solving that IVP, which just means plugging in those initial conditions and then solving for the appropriate value of the unknown constant. All right, let's go ahead and take a look at one more sort of basic example like this. So we want to find all solutions to the differential equation x squared y prime minus x squared cosine x equals negative x squared secant xy on the interval 0 to pi over 2. That interval is there just to avoid anything weird with like that secant, which could have some domain issues. So again, not going to be too worried in this class about domain restrictions. Sometimes you'll just see these intervals which are assuring us nothing weird is going to sort of happen. Is this linear? Well, y prime and y are in separate terms, no functions of the dependent variable, so linear, all good. We can go ahead and put it into standard form, need some manipulations. This guy should come here and this one should come over there. So it looks like we get x squared y prime plus x squared secant x y is equal to x squared cosine x. All right, so things are looking pretty decent there. Now it is in linear standard form. Is that actually true? Well, not quite. Why is it not quite in standard form? Because of that x squared there. We actually don't want anything in front of there. So I sort of misspoke. I spoke a little too soon, I suppose. It will be eventually. So this is still just linear here. We don't really need to make any comment. To actually put it in standard form, we need to divide by the x squared. So let's go ahead and do that. That's nice and easy because everything has an x squared, so it won't make things very complex. Secant xy, cosine x. Do we need to make a note of x not equal to 0? Well, again, normally we wouldn't even be that concerned because that's the independent variable. And we know we're on an interval where x is between 0 and pi over 2. So we're definitely not concerned about it being equal to 0 because we've got a soft interval there. We got that open parentheses. So no concerns about the x not being equal to 0. We can make a note of it, but it's not going to affect anything. Now, I can go back and actually say this is linear standard form here. So let's go ahead then and actually use our approach. So our integrating factor is going to be e to the integral secant x dx. So there's our secant x, that's our p of x. What is the integral of secant x? Well, it's a little bit of a messy one, but it would be e to the ln of secant x plus tan x. So secant x plus tan x is our ln of secant x plus tan x is our antiderivative of secant x. Then, of course, the e and the ln can cancel out. So it looks like we're getting secant x plus tan x as our integrating factor. So let's multiply that on both sides. So we get secant x plus tan x y prime plus, I guess, secant squared x plus secant x tan x y equals secant x plus tan x cosine x. Now over here again, very messy, but it should be a product rule of the integrating factor, which is secant x plus tan x times y, all differentiated. Let's check. Derivative of secant x plus tan x. Derivative of secant is secant x tan x. Derivative of tangent is secant squared, and then the y would be left alone. Good. And then we leave this part alone, differentiate the y, and we get that. So this is absolutely a product rule. On the right-hand side, we've got secant x plus tan x times cosine x. Now we can go ahead and integrate with respect to x. So on this side, we just get secant x plus tan x times y is the integral of secant x plus tan x times cosine x dx. At this point, we're going to have to figure out how to integrate this thing, but of course we can do a little simplification. We can multiply that cosine in there and get secant x plus tan x y is equal to the integral. Cosine times secant, of course, is just 1, and cosine times tangent. Tangent is sine over cosine, so we just get sine x dx. Now we can go ahead and integrate. Secant x plus tan x y is equal to x minus cosine x plus c after integration. And then I suppose if you really wanted to, you could divide this over, though I don't know in this case if it's that great of a choice, but we'd get x minus cosine x plus c over secant x plus tan x. And that right there, that would be considered our general solution. Every solution to our linear differential equation is going to be of that format on that interval 0 to pi over 2. Obviously, there were some moves like moving this over here, or like we said, dividing by the x squared up there, in which we would be concerned if we weren't on that 0 to pi over 2. But again, our class, not too worried about domain restrictions like that. So at this point, we've gone through and done about 4 different examples of sort of going through, I think it's been 4, 1, 2, 3, and 4. So we've done about 4 examples of sort of just this standard approach of identifying something as a linear differential equation, putting it into standard form, and then using this integrating factor approach. The last example I want to do is a little bit unique, just because it shows us that we don't have to be restricted to just all these sort of nice basic functions we've been doing. I want to do one example that sort of goes back and realizes that P of x and Q of x just need to be continuous. So we're actually going to work with a piecewise function and see how this approach can sort of be used here. Now, interestingly enough, I do want to make one comment here. The way I'm going to show you guys how to deal with a piecewise function, which is a very, very sort of special case, is a little bit different than how your textbook does it. Your textbook makes use of a dummy variable approach, which definitely works, but I find it a little messy when they actually go through and do an example of it in the textbook. So I want to show you guys a slightly alternate way. You're, of course, welcome to use either one. And again, do keep in mind that our next example is just a very sort of unique situation when dealing with piecewise functions. So let's go ahead and take a look. We want to find the unique solution to an initial value problem, so very standard sort of setup, but our sort of thing that's unique about it is that we're going to have where this right-hand side, or any part of it, is a continuous function, but it's a continuous piecewise function. It's that absolute value x minus 1. So we're going to see how to do this, but to start with, let's go ahead and just remind ourselves what we can actually say about this absolute value x minus 1. And do keep in mind that absolute value x minus 1 is not a differentiable function, right? It has that sort of V shape, and it has that moment where it's non-differentiable. But it is continuous, which means that according to our sort of discussion at the beginning, as long as the P of x and Q of x are continuous, you should be able to solve these. So even though it's non-differentiable, we can still go ahead. So let's just remember that absolute value x minus 1 really disguises that this thing is a piecewise function. Keep in mind that this is equivalent to x minus 1 when x is greater than or equal to 1. So when x is greater than or equal to 1, obviously this is positive, so the absolute value doesn't do anything. And it's equivalent to negative x minus 1, which of course is 1 minus x, when x is less than or equal to 1. And of course, again, like we said, this that's the definition of the absolute value function, right? So it's just hiding that it's really a piecewise function. So what we're going to do is we're going to approach this in our sort of standard way. We should be able to see that this is linear and in standard form. So there's not going to be any manipulations. It's just a little bit weird over here. But we're going to break it down into two cases. We're going to sort of break it into pieces when we're talking about values of x that are less than or equal to 1 and when we're talking about values that are greater than or equal to 1. So let's have our case 1 here, where x is less than or equal to 1. So in that case, we're really working on y prime equals plus 2y is equal to, well, since x is going to be less than or equal to 1, we're going to be using this piece over here, which is negative x minus 1. All right, let's go ahead and we can simplify that 1 minus x. Let's go ahead and find our integrating factor. Our integrating factor is going to be e to the integral 2 dx, because our 2 is our p of x here. That means our integrating factor is going to be e to the 2x. We can go ahead and multiply that on both sides. E to the 2x y prime plus 2e to the 2x y is equal to e to the 2x minus x e to the 2x. All right, left-hand side should be a product rule. So let's just confirm e to the 2xy prime. Derivative of that e to the 2x, yep, that's 2e to the 2x. Derivative of the y is going to give us that term, so we're all good. Equals e to the 2x minus x e to the 2x. Let's go ahead and then integrate both sides with respect to x. So we're going to integrate with respect to x. So e to the 2xy is going to be the integral e to the 2x minus x e to the 2x dx. Now, we could go ahead and do this as two separate integrals and then use integration by parts on this. Turns out we can be a little bit clever and refactor and then just do integration by parts once. So I'm going to sort of recognize this as integral 1 minus x e to the 2x dx. Now I can do this as an integration by parts where I'm going to let the u be that 1 minus x and the dv be e to the 2x dx. du is going to be negative dx then, and v is going to be 1/2 e to the 2x. If we pop that stuff back in, we get e to the 2xy is going to be u times v, so 1/2, 1 minus x, e to the 2x, minus the integral of v du, since there's a minus it becomes a plus, 1/2 e to the 2x dx. Finish up this integral here, and we get e to the 2xy equals 1/2, 1 minus x, e to the 2x, plus 1/4 e to the 2x plus c. All right, then we can finish up, divide by that e to the 2x, and looks like we should get y is 1/2, 1 minus x, plus 1/4, plus c e to the minus 2x. All right, so this is sort of what our solution should look like when x is less than or equal to 1. Now we're going to do a second case, and it should be very, very similar for when x is greater than or equal to 1. So case 2, x greater than or equal to 1. So now we're going to have y prime plus 2y is equal to x minus 1, because x is going to be greater than or equal to 1, so we're going to have this on the other side. So let's go ahead and use our integrating factor. It's going to be, of course, the same thing, because we're only changing the right-hand side, so we're going to get our e to the 2x. We'll get e to the 2x y prime plus 2 e to the 2x y is equal to x minus 1 e to the 2x. This guy is going to be the exact same product rule here, so e to the 2x y and then prime is going to be x minus 1 e to the 2x. We do our same integration with respect to x. So e to the 2xy. Notice most of the stuff can just be reused. So the idea is that the integrating factor in that component isn't going to change. It's just that we're rephrasing the right-hand side, that q of x, depending on what piece we're on. So now we're going to get the integral x minus 1 e to the 2x dx. It will again be an integration by parts. U is going to be x minus 1. dv is going to be that e to the 2x dx. du is going to be dx, v is going to be 1/2 e to the 2x. So we get e to the 2xy. This uv is going to be 1/2 x minus 1 e to the 2x, and then minus the integral 1/2 e to the 2x dx. And then we can finish that up, and we get e to the 2xy, 1/2 x minus 1 e to the 2x minus 1/4 e to the 2x. Okay, first thing that we should be careful with here, we probably don't want to put plus c because it might be a different constant of integration, which we'll talk about in just a moment, than here. So what I'm going to do is I'm going to say plus d. And then we're going to go ahead and divide our e to the 2x over. So y equals 1/2 x minus 1 minus 1/4 plus de to the minus 2x. Okay, let's give ourselves a separate sheet and sort of finish this up here. Yeah, there we go. That's what we're trying to do. So we have case 1 when x is less than or equal to 1, which we did here, and we got this. I'll just grab this and bring this over here. Okay, so just summarizing what we got here. And then we also did case 2, which is when x is greater than or equal to 1. So here we went through and we got all of this. Okay. Oh. Okay. Put that right there. Okay. So remember, we're trying to solve this IVP. Now, in general, this is the moment where it gets a little subtle. These constants, if we weren't interested in solving an IVP, would be defined in such a way that you would choose this constant, say, to make sure that at the point where you change from x less than or equal to 1 to x greater than or equal to 1, that you would assure that there's continuity. We need our solution to definitely be continuous. So what we would say is, if we really wanted to, we could solve for this d constant in terms of c by plugging in the moment where we switch, x equals 1, plug it in here, and then set the two equations equal to each other and solve for d in terms of c. Because this constant basically has to be chosen to assure that the two pieces are continuous. But we don't need to solve in general. We want to solve this initial value problem. So we can actually use this to determine one of the constants and then determine the other based on the first one. So how do we use this? Well, we need to pick out the correct case. This initial value actually occurs here for case 1. So for the initial value problem, y of 0 equals 1, meaning x is 0, y is 1. This applies in case 1. So let's plug in x equals 0 and y equals 1 in case 1. So we get 1 is 1/2 times 1 plus 1/4 plus c. Then I guess we can put that together. That's going to be 3/4. Bring that over there, and it looks like we should get 1/4 is equal to c. Okay, so we actually know now that for case 1, for x less than or equal to 1, our solution should be 1/2, 1 minus x, plus 1/4, plus 1/4 e to the minus 2x. Now, how do we figure out what the choice of constant for case 2 is? You might say, can't we just let it be d, the unknown constant? Well, of course not, because it's a unique solution. There has to be a correct choice of this. So we find value of d by continuity. So what we need is we need to make sure that when we transfer at x equals 1 from this part to this part, those values are equal, so it's a continuous, basically, switch. It's going to maybe not be a non-differentiable part, but just like a V shape, right? It's a continuous switch in terms of value, right? The value from this piece and the value from this piece are the same. So what we do is we're going to evaluate case 1 and case 2 at x equals 1. So in case 1, we now know that that would be 1/2 times 0 plus 1/4 plus 1/4 e to the minus 2. And we're going to set that equal to evaluating this at x equals 1, which would be 1/2 times 0 minus 1/4 plus d times e to the minus 2. So we should now be able to solve this. We can bring this over here, and we should be able to get 1/2 plus 1/4 e to the minus 2 is equal to d e to the minus 2. Multiply both sides by e squared. 1/2 e squared plus 1/4 is equal to d. So that means our unique solution is this piecewise function. It is the piecewise function 1/2, 1 minus x, plus 1/4, plus 1/4 e to the minus 2x, when x is less than or equal to 1. That's the choice of c that satisfies the initial condition. And then for case 2, it's 1/2 x minus 1 minus 1/4 plus 1/2 e squared plus 1/4 e to the minus 2x for x greater than or equal to 1. If you guys want, you can confirm by checking directly or by using like a graphing software or something that this is a continuous function, that at x equals 1, even though we switch from this piece to this piece, the value at each side will be the same, so it's a continuous function, and this does satisfy the differential equation. So again, this is a very specialized type of problem, what to do with a piecewise function. We're not going to really encounter this too much. To be honest, differential equations and piecewise functions are sort of hard to mix together. There's a theory developed sort of towards the very, very end of this class that we might briefly talk about called the Laplace transformation, which was actually created to deal with situations where you have differential equations and piecewise functions because of the messiness of trying to do it manually like this, having to break it down into cases. Keep in mind we'd have to have more cases if the piecewise function had more pieces. So this is not something we're going to really encounter too much, but your book does go over one example of it. I wanted to go over one as well, and I wanted to do it in sort of an alternate way just so you guys had two approaches when dealing with piecewise functions. For now, this is going to wrap up section 1.6. In our next video, we'll move into section 1.7, which looks at some applications of these linear differential equations.